Hello there, welcome back to our channel and let us analyze this circuit. So as you can see, the circuit consists of the BJT, which is an NPN transistor, and this is the collector pin of the transistor, this is the base pin of the transistor, and this is an emitter pin of the transistor. So this is a single stage amplifier, and the circuit is biased in the common emitter configuration. The input is applied across the base and emitter, and the output is taken across the collector and the emitter. And there are 2 points where the output can be taken. One is from the collector is VO1, and one is from the emitter is called VO2. There is a resistor RE called as emitter degeneration resistor. In the absence of this emitter resistor, the gain of this amplifier is simply the product of resistor RC and the transconductance GM of the transistor. That is the output. In the presence of resistor RE, the gain is independent of the transconductance parameter of the BJT, which may vary with the temperature. And now with the RE available in the circuit, the gain of the circuit is given by the ratio of RC over RE. RB1 and RB2 are used to set the DC bias level of this transistor. This acts as a voltage divider circuit, and that sets the base voltage of the transistor. Vs is an external voltage source with its resistance in series Rs. In order to analyze the operation of this circuit, we often tend to obtain the small signal model of the circuit where the DC voltage sources are connected to the ground, that is the AC ground, and then we apply a Thevenin's equivalent circuit rule to this to obtain the Thevenin's voltage VTH and the Thevenin's resistance RTH, and from that we obtain the various operating point or the bias points of the circuit. Ultimate goal in order to use this circuit as a small signal amplifier is that you make sure your transistor is biased in a linear mode or active mode, which demands the base emitter junction should be forward biased and the base collector junction should be reverse biased. And the output signal VO1 and VO2 are available as I indicated before. So here you can see the small signal model of this transistor. This is a voltage source Vs with its equivalent series resistance Rs. You have the transistor B, that is the base terminal, then that's the collector terminal, and then that's the emitter terminal. From emitter to the ground, you have this resistor Re, which is shown in the circuit. Now, you have RPI, that is the resistance between base and the emitter of the transistor, and the voltage that you generate across the base emitter is VPI. The collector current is dependent on the applied input voltage, that is VPI, and the final collector current is the product of transconductance GM into VBI, and this is the dependent, it is modeled by a dependent current source as shown. Now this current is flowing as output current, and the load resistance RC is connected between VO2 and the ground. Now there is a voltage source applied. Therefore, the current I in flows into the circuit and it tries to go into the base pin of the transistor. As you can see, it goes into two parts. goes into the base and goes into the parallel combination of RB1 and RB2, which is the Thevenin's equivalent resistance RP. And I in minus IB is the value of that current which flows through RP. Now, if you look at the from the input side into the circuit, you get the input resistance of the circuit. If you look at the output from the output side into the circuit, you get an output resistance of the circuit RO. And if you look at the circuit from the RC, this side, you get RO dash, which is again the output resistance of the circuit. As I said, from the collector, you can have output voltage VO1. And as I said, from the emitter, you can have another output voltage VO2. So this is how you can obtain a small signal model for this circuit. This is the original circuit and this is a small signal model. So hope you understand this video, and if you did so, share with others.